All right. I believe this is the last day of class this semester for this class. I think you can still have classes on Thursday and Friday. And that's cool and good. I am once again announcing that you should stop writing code by 5 p.m. on the 9th, which is in 6 days. And that I will be around for 3 hours before that is due. High degree of availability. I was not planning to be here in person. If a bunch of you in Discord, if 6 of you are going to be here or something, let me know and I'll come down. I don't mind. But I expect you're probably going to want to work on this wherever it is you write code, and for me that's in a dark room by myself. Wait, no, oh no, I wrote very good slides last night and then did not share them, which is going to significantly complicate today's lecture. That's okay. All right. I guess we're doing a board talk today. Oh, there are there? Are they called? Oh, I just didn't refresh. Crazy. Okay, thank goodness. Okay. I'm quite happy with these, so I'm glad they're here. Always hard refresh, folks. Okay. I didn't put hashing in the reference solution. It didn't seem interesting to do that in Python, so I just didn't do it. Today we're going to cover the things that I did not cover last time. I am thinking of this as bonus content. It is real interesting, though. So that's what we're doing today. Hashing. Okay, so here's the deal. Some of you have realized this, and especially those of you that knew what happened last semester realized this happened. This was also an intro security course, and I just didn't tell you. And the reason I didn't tell you is intro security is kind of boring, so I didn't really worry about it that much. But it so happens that through the process of doing the hashing and implementing the systems code and stuff like that, you basically know how to do secure computing at a high level of abstraction. The low-level implementation details are beyond anyone's knowledge. They're an active research area. It is unclear if computers even can be secure. It is unclear if we can precisely define security. There are theoretical frameworks that are approaching this problem, and none of them are mature in my view. That said, this matters a lot, specifically if you are, I would argue specifically if you are Git. But in fact, the early people that were using Mercurial and SVN before they were using Git were all writing enterprise software, and they were selling their software to Lockheed Martin and the National Institutes of Health, right? And it was relatively important that that code was correct and wasn't just bleeding personal data all over the internet or something, right? So when you're working with source code management, you should probably care a lot about when someone changes between different versions of commits, that they're actually going back to the historical commit they think they are, and that no one has tampered with the relatively small amount of text that they have to tamper with in order to cause there to be a fairly serious form of bug, which can be a malicious security vulnerability, or it can just be a functional problem, right? So I'm going to say that there are two big risks that we are going to guard against using the optional extension to the final project. And these are integrity, and I'm going to call it confidentiality, but I'm going to stretch that word to its absolute limits. Integrity means once I have written some version of source code, once I have placed that version of source code under control management using some command, or perhaps I just have a background process running or something. So once in my context I use commit, it should become impossible, or at least infeasible, so highly unlikely, for someone to change any portion of that code without it being obvious that it's been changed. Now, it could be the case that it is permanently destroyed, right? That is difficult to prevent. But it should be extremely, extremely difficult for someone to go back in there and edit an API key. So I'm now reaching out to a malicious service. It should be extremely interesting for someone to go back and put in a debug call that leaks my private key. All of these things should be extremely difficult to alter. So I should have a trustworthy historical record of the changes that my source code passed through, and we refer to that as having integrity. That is mostly going to be accomplished with SHA-2, because we're just going to hash these things. We're going to save the hashes, and then we're going to check the hashes. And by the hash being consistent with the source code, then we will believe that we have achieved integrity. Is this absolutely certain? No, of course not, but it is comically unlikely that it is not the case. Then we're also going to have confidentiality. Confidentiality is signing commits. It is hard to get excited about this with your own source code management system because you're probably going to be using it with yourself, and you're probably never going to be giving it to anyone else. That said, ED25519 is a cool piece of technology, and it was made to solve this problem, so we're going to use it. Specifically, what we're going to use is every commit is going to have attached to it some user that made the commit. And we're going to have extremely high confidence that that user made that commit because they're going to release their public key, and they're going to do something sneaky with their private key that only they can do. And we will verify using their public key that they did the sneaky thing. And then we will know that necessarily whoever made that commit must be the owner of that public key. And so this will give us confidence who is making changes to the code, and that the things that we think are the changes to code are exactly what are made. This is 2/3 of sort of the entry-level understanding of security, which is the CIA triad, which is good enough for anything. Availability is the last thing, and availability just means that the servers stay online, right? It's a little bit different, and we can think about, like, a lot of the performance engineering costs are going into this. I think fundamentally the consideration I made to availability was what I talked about last time, which is that I cache the latest version of the software no matter how high the memory cost is. And why do I do that? I do that so I can always make changes to my source code quickly. That makes it much more likely for me to not be taken offline by my system going down while it's going through some operations. Usually it's difficult to teach availability separately because availability is sort of not purely a security concept, right? But it is important in one way, which it is very easy to make sure no one ever finds your private key, which is to simply never generate one. But then you can't perform any public key cryptography, right? So availability forces you to have confidentiality and integrity over some service. So the functional specification that I provided to you, we can argue is available. This term, the two state-of-the-art technologies that we introduced are each solving one of these two problems. SHA-2 is solving integrity. ED25519, which there's got to be a better way to say that. I'm so tired of saying that. Some people say ECDSA, which is like not quite the same thing. These accomplish integrity and confidentiality. And of note, we use integrity within the efforts to solve the confidentiality problem because SHA-2 is a component of ED25519. I believe it is correct to say this, but I'm not a practicing security practitioner, and I use practice there twice to emphasize that I am not in the application domain. I claim these are both widely known with no known weaknesses. I do know they are open source, which offers a form of security. It might not be correct that they are widely known with no known weaknesses, but no attack has been disclosed over any of them so far. And just to sort of review this and drive this home, I have used motivating examples to motivate these sort of security contributions of each of these. And for SHA-2, that was always you download an operating system, and then you're going to put the operating system on your device, and it's going to have root access to your device. It's going to be able to do whatever to your device it wants. You really, really want to have high confidence that that's not a Bitcoin miner that's mining Bitcoins for cyber criminals, right? And the way you do this is you download the operating system and you hash it, and then you go to a website you trust, and there's a problem there, right? But fundamentally, that's the best we can do. You go to the website you trust and you check that the hash published there is the same as the hash you have, right? And so then at least you know either the adversary has completely taken down that other website, or if you get a hash disagreement, you can know not necessarily that there's definitely something wrong with your code. Usually what I find is that I hashed it incorrectly, right? But you can check that the thing you downloaded is what you thought you downloaded, right? And so you still have to go to the correct website, and you still have to do all of these things, but you can have higher confidence. The motivating example I used with ED25519 was the Snowden example. That is not how we're going to use it in the final. We're going to use it to do something different. Digital signatures and public key cryptography use the same algorithm, but they solve a different problem. So we're going to introduce the notion of digital signatures separately. I'm going to fidget with this because it's bothering me. There, that's more fun. Okay. RSA is the public key crypto system that existed before ED 25519 became dominant. And in fact, even just while I was prepping these slides and I was trying to look for examples of how to show you digital signatures, virtually all of those examples were still referring to RSA. I have only ever generated an RSA digital signature. It's just, that's all I've done. RSA was not intended for use with digital signatures. It is bad at it. It is slow and expensive. It introduces these unexpected security vulnerabilities, which is if you start digitally signing too many things, it is likely you will accidentally give away what random number generator you are using to generate your private key, which makes it much, much easier to determine your private key. So it is actually unsafe to sign things with RSA, and this was discovered usually after people signed a lot of things. ED 25519 has none of these weaknesses. It was specifically optimized to work for signatures, and it happens to work for the other thing. If you just click on any of these links and just go to the, wow, that is very zoomed out. What was I doing? When ED 25519 was introduced, it was basically introduced for signatures and is incidentally able to encrypt messages, right? This was designed to solve the signature problem and happens to solve the message problem. So it is good at this thing rather than being good at the other thing. And look, some of them are from the Midwest just like us. Anyone love the Midwest? Bears, Cubs, Sox, Bulls, right? Chicago? No? Okay, all right. I tried. What were we trying to decide yesterday? Is Pittsburgh in the Midwest?
Where's Pittsburgh?
That's what I asked. You think so? You think it counts? I think it's in the Rust Belt. What do we think about that?
It's in Pennsylvania.
Yeah, what's wrong with Pennsylvania?
Pennsylvania is not the
It's a little bit
Midwest.
too northeast to be in the Midwest.
So you're saying Pittsburgh is an East Coast city?
Well, it's a
Yeah.
northeast city.
Considered northeast.
Not East Coast, because it's not on the coast.
I prefer to refer to it as the least coast. Okay.
Well, I like the East Coast.
Well, in that case, you should refer to it as the Beast Coast.
Mm-hmm.
Okay. All right. So this is our old example of ED 25519. I promised that digression was intended and made sense. Okay. I'm imagining I want to whistleblow, right? I have some confidential information. What is it? I don't know. I don't even know what you could publish that would get someone mad anymore, right? Like Pepsi doesn't use real sugar. I don't know. Okay. Here's something that was actually upsetting to me. So I was drinking a real sugar, either Coke or Pepsi, and someone with a doctorate, who I actually believe, was like, you know that it's chemically identical whether they make that with corn syrup or cane sugar, because once you reach the form of pH that is present in the bottled or canned product, it causes the homeostasis to be achieved at the exact same chemical compound, whether you start with a corn syrup or cane sugar donor. And I know that's not true because they taste differently after I can see the label. So science hasn't gone far enough, right? But okay, so this is the example we used. I've got my little email from the CEO of Pepsi that says we weren't using real sugar the whole time. We did this specifically to trick Calvin. And I'm like, oh no, I got to get this published in the Oregonian, right? So I email my person at the Oregonian, newstips@oregonian.com. And I was like, wait a minute, I can't just send this or Big Pepsi will have me assassinated, right? So I instead don't send it. I actually just send a file called bigsecret.txt that's a stream of random characters, right? Because I encrypted it using the journalist's public key, right? And then when Big Pepsi tries to read this, they only see the stream of random characters, and they don't assassinate me, right? And I get to teach operating systems next term, which is actually my purpose in life. That's why I was put on this earth. A lot of people don't know that. So I encrypt the payload, and then I transmit, and then I hope that the journalist realized that I base64 encoded this before sending it over the wire, and not that it's actually just gibberish, because I forgot to say I base64 encoded it, but you have to do that to store it as plain text, right? So the contents of the payload are confidential. So Big Pepsi cannot read the message I sent, but Big Journalist can. And this is a form of confidentiality. Yeah, I can be standing right in front of someone. I can say something in code to someone else, and only the person that has the correct public key can understand what I'm saying. That's not what we're doing with source code management. There's this other thing that can happen is maybe you're like a high-ranking government official, or maybe you're the scientist that invented cane sugar, right? And you want people to know it was you when the leak comes out so they can have confidence in it. Confidentiality, confidence, right? So what do? I take the message from the Pepsi CEO, and I sign it with my private key, and then me, a professor who everyone can trust, I post the public key in my bio on X, the Everything app, right? That even hurts to say. I posted it on Twitter. I put it on my Tumblr. Okay. I put it on my Strava file. Any Strava people? Apparently everyone in their 30s is really into Strava now. Yeah, okay. So I put it, I tattoo it on my forehead, and then I scale the Empire State Building, and I get on the front page of the New York Times. Okay, right? So everyone knows it's my key. So this message comes out, it goes to some journalist, and the journalist is like, oh, I don't know what this is. I don't know how to decrypt it. This isn't signed with my private key. I was like, you have to use the key that I tattooed on my forehead before scaling the Empire State Building. And so then they look at the front page of the New York Times, and they type it in. They decrypt it, and it says, Pepsi Cola was not using real sugar the whole time. We did this to personally spite Calvin, right? And maybe people don't believe that message is actually from the Pepsi CEO, but they know who I am, so they know it's at least from me. And then they can make their own decision about whether to trust it based on knowing who provided that message, right? This is the other case. It is digitally signed. You can determine who sent the information. So the ownership of the payload is what we have confidence in, not the contents of the payload. We know who wrote the thing down. So I'm going to call this confidentiality of ownership. I've never seen anyone else call it that. I just had to call it something. We're going to call this a digital signature. And now I'm going to introduce a companion textbook for this class that has been the secret companion textbook the whole time. It is called CryptoBook. This is from a graduate course in applied cryptography, and these people are at one of the schools in California. There's a lot of schools in California, so it's hard to keep track of all of them. And they open sourced their graduate cryptography course. I don't really think graduate students have anything special about them that makes them better than the rest of us. So I just teach graduate cryptography instead of undergraduate cryptography, and you all seem to be doing fine. So if at some point this class you were doing ED 25519 and you're like, this seems hard, that was the haters trying to trick you that it was a graduate level concept, right? Just don't believe the haters. They don't know anything. So in this book, there's a way of teaching about things, and I'm going to follow that teaching style to introduce signatures. The crypto book likes to use this idea of attack games. And what is an attack game? You have an entity that is trying to accomplish some goal, and you have an adversary that is trying to gain access to protected information, or basically somehow defeat the entity. So you have someone who's trying to do something securely, and you have someone that's trying to cause things to be insecure. And here we use the term the attacker. So we are going to... Did I skip a slide? No, okay. Here's what we're trying to do. I'm trying to get the message out that people know that I published, and an attacker is going to try and impersonate me. They're going to try and make something that I did not sign that looks like it was signed by me. So we're going to call this a chosen message attack. The attacker is going to try and decide which message they want it to seem like I said, okay? So they generate a message, they do some algorithm to it, and then it looks like it's signed with my key. And the attacker does not have access to my private key. So this is, how secure is this thing if they don't have my private key? So what we want is, even if the attacker can get anything signed, they should still not be able to create a signature on something that I did not sign. This is, what is this? A valid message pair. So this is the message. So that is, for example, saying Pepsi is as good as Coke, which I would never say. Unless I can't see what's on the bottle, then I don't know, right? And this thing is the signature, which is, that's just a series of characters that is, if I take Pepsi is just as good as Coke, and feed it through my encryption algorithm using my private key. So no one else could generate that number. So for a given signature scheme, and what is a signature scheme? We generate keys, so that's G, and this is like script G or something. I don't even have any idea how I made that G. I'm going to generate some keys, my public and private key, then I'm going to sign some message, and then someone else is going to verify the message, right? Anyone can verify the message using my public key. And we're going to define that scheme over messages and signatures. So what is this? This is big M and big sigma. That corresponds to little m, and I'm guessing this is supposed to be little sigma. Does anyone know the Greek letters? Do any of you know what that is? I think it doesn't look like little sigma to me, but this looks like big sigma to me, so I'm assuming. Anyways, this is the set of all possible messages I could send. Sorry?
Little sigma's like a circle.
It's omega.
Oh.
It looked like omega to me.
You're right.
Should there be omegas in big sigma? Instead of saying big sigma, I like to say big sig. I feel like that's like a fun thing to say. Like, oh yeah, my favorite letter, it's big sig, right? Okay, so there's a universe of possible messages I can send. Usually this is every possible string up to some length. And for every message in that universe, there is some signature, which is what happens if I take that message and I encrypt it using my private key. Usually we encrypt things with public keys to transmit them. I'm encrypting it with my private key, so it can be decrypted with my public key. There's going to be a given adversary, A. And what is the adversary going to do? Well, first we're going to generate the public key, and SK here is denoting secret key. I find it really, really hard to deal with the fact that public and private both start with P. I haven't come up with a good solution to this, so here we're using public verifying key. I don't know, right? Okay, and so what are we doing? We're sending the public key to the adversary. Okay. The adversary is going to query the challenger several times. So we're going to send in a bunch of messages, and we're going to get all of them to be signed. So what is this? There are many messages. The messages are in the universe of messages that we made. And each time we are going to, for that message, we are going to figure out what. Yeah, this is definitely supposed to be little sigma, because that's a little sigma, right? That's what we think sigma is? Is that sigma? Physicist. Thank you. Thank you for taking physics. You all should have to take physics, and I'm going to die on that hill.
We do have to take physics. Or chemistry.
Yeah, one of them.
Yeah, or chemistry, right? Yeah. Wink. Okay. It's not a lot of seats in chemistry. Here, watch this. So I always look up the CS classes. So when I type in CS, and then you just change this to chem, right? Oh, how'd registration go? Is everyone registered okay?
Yeah.
Okay, let's look at Chem 116. Spring. There's 23 classes. Wait, no, there are seats. I was told there weren't seats in any of these classes. Everyone just wants to take this one. Never mind, you can totally take chemistry. Go ahead, you can take chemistry. That's fine. Let's look at physics real quick. There's seats in here, you could take chemistry and physics. Do you know how smart you would be if you knew both of those things? I barely even know calculus, and I've convinced people to let me be a professor. Okay, so what are we doing? My adversary is allowed to use chosen message attack, which means I can get the signature of anything. So I get, for as many messages I want, I figure out what the signatures are. That's what this is. Given MI, the challenger computes the signature which corresponds to the message, and then the adversary gets the signature that corresponds to every message. So what am I trying to do? I'm trying to see if by looking at a large number of signatures I can determine what the private key is, or determine some other weakness of the algorithm, right? Okay, now, what am I going to try and do? Now the adversary is going to try and impersonate me and say that Pepsi is as good as Coke. And I want to note that I am not sponsored by Pepsi. Specifically, I drink approximately 16 servings of Gatorade a day, and they have not sponsored me yet, and they're owned by Pepsi, right? I'm doing this challenge called running, and I no longer consume solid food. I'm living off of entirely Gatorade, which is a combination of dextrose and maltodextrin. I looked it up, and I tried to make my own at home, and Pepsi Pepsi is so powerful. They sell me Gatorade at a cheaper per calorie. This is not related to anything. At a cheaper dollar per calorie rate than buying my own maltodextrin and dextrose and mixing it together at home, which I know because I bought those two things and I mixed them together and then I figured out how much. And I was losing money making my own Gatorade at home. So, anyways, I love Pepsi, the company. That's not true either. Okay. So, anyways, someone is trying to get me to say that Pepsi is as good as Coke, and how do they do that? They study a bunch of the things I signed, right? So I've been signing all kinds of crazy things. I've been signing things that say, like, taxation is theft. I've been signing things that say, okay, don't take this out of context. Stalin did nothing wrong, right? Like, and so, like, I've been signing all sorts of nonsense like that, right? And so, okay, I'm done with all of that, and then what happens? Okay, surely now we can say Pepsi is better than Coke. So we have the message, and we generate our best effort signature, and the attacker is successful if that is the correct signature. So the signature is a member of this set, which is the set of things that would be generated by my signature generation scheme. Okay. So we say the adversary wins the game if the following two conditions hold. That the message is accepted given whichever key this is, the public one, and that's bad. Okay, so how are we going to apply this to the specific use case of working in our source code management technology? We're going to check what time it is. Oh, we're doing great on time. Folks, we're cruising. So I'm running now. There's these things called cruise intervals that I read about in Exercise in Health Science. I can't figure out what they are. They're just referred to as cruise intervals. And then I was wondering if they were referring to like the queer lifestyle cruising, and I didn't want to look it up. So anyways, if you're looking for something to study over winter break, try and figure out what cruise intervals are. So anyways, Merkle tree. You all remember Merkle trees, right? They're trees made out of Merkles. That's not true. They're trees made out of hashes, but we call them Merkle trees named after Merkle. And I don't know who Merkle is, and I was going to check and I forgot. So how are we going to use a Merkle tree? We're going to go over it. Okay. I think the big thing that can go wrong with an SCM is a historical commit is corrupted, and then someone checks out that historical commit, compiles the code, and tries to use it for something. The compiling code step is like a little bit sketchy because I gave you a demo example in Python, so it doesn't actually compile. But, you know, it makes perfect sense. So what am I going to do? I'll write some code. The code is my total ordering of cola companies. So you got RC Cola way up at the top, right? And then under that you have Coca-Cola. And then under that you have Pepsi Cola, right? And so I write that and I commit that to my repository. And then I write another 4,000 commits of code, adding a variety of features such as my total ordering of orange sodas and also my total ordering of little coffees, right? I have a total ordering of alternative plant-based milks, right? Which is, let's see if this is controversial. So soy number 1, right? Okay. Oh, well, okay. That was controversial because 2 people nodded and 2 people shook their head. And I was only looking at 4 people. Second is macadamia. Oh, wow. I'm starting fights here. Okay, then we have oat. Okay. And then almond is not milk, right? Okay. Cashew milk. Nominally, you can make milk out of peanuts, but you have to do it yourself, and then it costs more than the Pepsi Cola stuff. Okay, so anyways, I got my ranking of plant milks. I commit that, and I've already committed RC Cola, Coke, Pepsi, right? So I keep writing code, and then I realize, wait a minute, alternative plant-based milks don't qualify as a soft drink. I shouldn't have put them in my soft drink tier list repository, right? So I decide to go back to when I had my rankings of different sodas, and I go back and I'm looking at this and I'm thinking, why does it say RC Cola, Pepsi, Coke? I don't remember saying that. That's the bad thing that can happen, right? So this is pretty easy if you're missing a line in a diff or something. For example, probably I have a list somewhere that just says RC, Pepsi, Coke, and it's just easy to get those lines out of order. Certainly, probably when you were all writing diff, if you ended up doing it the way I did, you pop a bunch of lines onto a vector and then read them out in reverse order. Very easy to accidentally put things, if like the only thing going on is you're putting 2 things in order, it's very easy to just like not reverse 2 lines by accident, you know? If you have an off by 1 error in a for loop or anything like that. I want to give you some other examples of like ludicrously bad things that happen. So this semester we have not been teaching you to write code that is suitable for use in a production environment. This is not a software engineering class. If it were, you would have been extremely banned from ever writing Unwrap. And why is that? You all remember guest speaker Jimmy, right? Jimmy told me, and I'm assuming this is true, that was the most popular class of this semester, which is interesting because I've been pouring my heart and soul into all of these classes, and then Jimmy just cruised in, and you all liked him better. So I want you to know that didn't hurt my feelings, and also, I'm supposed to give you time today for the course evals. Just fill it out, assuming that whether you like Jimmy or I more, whichever one you like more, that was the course instructor, right? Okay. So Cloudflare, which is big, but I'm not sure how big. I think of them as a semi-permeable membrane between a lot of web traffic and then the big providers, which are Amazon, Microsoft, and Google. So I think they sort of provide a service in there, and they're trying to push into the space of being one of the sort of the big three, which to me seems economically impossible. But I guess I wish them luck. I don't know. When you are assessing the relative virtues of a cloud provider like this, a good thing to do is to look into why certain entities are gravitating towards usage on one of the non-standard providers. To the best of my knowledge, Cloudflare kept up some websites associated with, I'm going to say fascism, that other cloud providers would not keep online. And then the question you have to decide is it good that they're not doing content moderation, or is it bad they're hosting websites that Amazon thought were too risky to hurt? And so look it up and make your own mind. But anyways, whatever else they're doing, Cloudflare has some underlying technology that is quite interesting. But they disclosed as a result of an outage on November 11th, Armistice Day, that someone, and what is this? That's the Git logo right there, by the way. I don't know if you can see that. So this is a Git commit. And this Git commit has one line in it that contains an unwrap. And what happens if you put an unwrap in production code and then you hit this line of code? Oh, Cloudflare goes down, and with it, 70% of the internet. Right? So, when the bad file with more than 200 features was propagated to our servers, the limit was hit, resulting in system panicking. The Rust code that makes the check was the source of unhandled errors shown below. So, someone put one unwrap in actual real code that like a grown-up was going to use, not like us, and it instantly crashed the entire internet. So, that seems bad. So, like, maybe don't commit this version to version control so you don't revert to it by accident. I would encourage, and I'm not going to require this because of the type of class we're in a final for a class like this, you should have no unwrap calls in your final project, right? Because you should be dealing with all of the cases that can handle gracefully without crashing, right? Is it just like kind of painful and not algorithmically interesting to write all of those? Yeah, so like go ahead and use unwraps if you want. But as an academic exercise, you should at least have a plan for what you would do. And usually what you're going to do instead is you're going to have a match, you're going to print something graceful, you're going to exit gracefully. You're going to ensure, for example, that if you had the SCM file open when you hit this unwrap, that you write something back to it that's eventually consistent, right? So you might have an exit routine or something like that. Maybe some of you have seen, there's this like @exit library in Python that is used within PGL, which is used in CS1, which like does a bunch of like graphics cleanup. So this thing's been around forever. Okay, so that is an example of a bad line. I'm not going to show you an example of this, but especially when people started vibe coding, you remember vibe coding being a thing? The vibe coded apps all just stored private keys in plain text and then checked them into public GitHub repositories. That was like a thing that was happening all the time. It was very, very easy to find, especially API keys in repositories for a while there. You had to like know to look at a repository. But anyways, that happens all the time. And then, of course, what did the amateur software engineers that were already vibe coding do? They pushed a new commit that removed the plain text private key, but the old commit was still in the version history, so you could still look up the private key, right? So you probably don't want to do that. And then I think I was trying to find an example of this, and I think there was one. I'm going to write it on the board so you can see how it's spelled. I believe the most used Python package in the world is Boto3. which is an internal Amazon package that's used to do some like data analytics or something in their background. Something a lot of, I don't know, like relatively nefarious people did is in Python. There's a lot of 2s and 3s floating around because most production services use Python 2 and Python 3 somewhere. And so sometimes there's simple find replaces on 2 and 3. So at some point in the past, and I can't find evidence of this, but I'm pretty sure this happened because I like remember hearing about it. Someone wrote a package called Bodo2 that like remotely hijacks an Amazon instance, right? And so like it takes control of one CPU. It's not a huge deal. And they just called it Bodo2. And then like a bunch of interns were writing Python 2 code, and they like didn't know Python 2 because they learned Python 3 in school, right? And so they're like, oh, I'll import Bodo 2 instead of Bodo 3. This one's maintained by Amazon. This one's maintained by like Big Evil. I guess that's the same as Amazon. Big Hack. Also kind of the same as Amazon. And so Bodo 2 got imported, and like every time you make a call to what looks like a Bodo 3, call in Bodo 2, it like mines Bitcoin on your system for an eighth of a second and then resolves, right? So this is the, maybe a single character can be changed to use a malicious rather than intended library. And so we use this library, CERD, which is how this is pronounced. Perhaps CERD, right? I feel like if you just called it SARD, that would probably sneak through. Or maybe that looks similar enough, I don't know. Or like maybe you have SEND. My handwriting is getting better over time, as you see. So it's easy enough to imagine someone writes something called send that has all of the same APIs as CERDA, and it just functions the same as CERDA, but it mines Bitcoin on your system for an eighth of a second before it returns any call. So I think this happens a lot. I found a Medium post to get about it, but I don't really know that I trust this person, and also they want you to spend money, so I didn't read it. Okay. Some things are easy and some things are hard. But it is relatively simple to compute the hash of a commit, and it is relatively simple to save the hash of a commit. But we have to not accidentally do something silly. And the silly thing that I was thinking I would be likely to do is I sort of had an inclination. It's like, oh, I should hash the serialized version of the commit. So I should hash with the thing that I called latest, which was the JSON file that contained arrays of lines of text. Why should I not hash that? Well, whatever malicious thing is going on could take place in between the internals of the SCM and the actual working files living on my physical system. So whatever I do, I should make sure all of the files are written to the local file system, hash them in place in the file system, because the thing that matters is the integrity of the files that are written in the file system, not of the internal data structure in the SCM. So because I'm trying to guarantee the integrity of the source code, I should verify the source code. Let's step through how I did this. This is not Rust, and this is not Python. This is a command line way to do this. I thought about giving you a reference solution that was actually written in Bash, because so many of these things are Bash supported. But I think we can take a look at this here. There we go. Let's see. Maybe I have something in temp, CS1. Okay, so this is what I was using in CS1 today for an example of how to use NeoVim, because I decided to teach them NeoVim. They got really upset about that, and on Friday we're going to watch Alien. So if you want to watch Alien with me and the CS1 class, and it's only the cool people are showing up to that class now, so it's actually a great time. So I'd recommend you show up at 10:20 or either we might try and start it early because it's a 2-hour-long film. So at 10:10 or 10:20 on Friday, in that room right over there, we're going to start watching Alien. So if you want to come be a bad influence, hang out. I might bring donuts. I'm not making any promises. You're invited. Okay. Oh no, I'm recording for this. Only the people that are here in person are invited unless they have a good excuse to be watching on stream. Okay. So, all right. So I was making this for them, and then I had to let them watch Alien because they were so scared of the command line, which, reasonable. We've all been there, right? Do you all remember being scared of the command line at some point? And you're over that now, right? Just like through sheer osmosis. Okay. Okay, some of you look like you're still scared of the command line, and that's valid. Okay. So So what can I do? Well, I can cat things. I can cat, I can cat tax.py. We've seen this before. I can find things. And when I find things, it gives me the names of files in my directory. If I go back up and I find here, I get a whole bunch of stuff. But what is something that is really annoying I get? Get a bunch of git stuff. Ew, right? So how do I solve that problem? Well, if I find star, it doesn't show hidden stuff in the current directory. It looks like I get recursively hidden stuff. But let's go into cd skim. Okay. What was I doing in here? I taught this in class on Monday, and I have no memory of it. Okay, so let's look at find. Bunch of hidden stuff. Let's get find star. No hidden stuff, right? The hidden stuff has gone away. But the other thing that we might want to do is we might want to only look at files. And so this is only files. There's no directories here. And this is useful if you're hashing things because you don't really want to hash a directory. Let me show you an example of this. So for example, I can hash a file. I'm going to hash skimpy. How would you pronounce scm.py? Is it scampy? It's schemappy. That'd be an A, right? Schemappy. Okay, so we can hash schemappy using SHA-512-SUM, or of course we wrote the Rust version, which I probably have on this device somewhere. Scampy. .py. There we go. And so I can get the hash of that file. Now, if I try and hash a folder, it doesn't work. So, if I'm hashing things, I want to hash the files. So let's go back into Scampy. Let's find star type F. This gives me all of the files. That looks like there's an F on that line. I'm going to, can I unlittleify this? Oh, I can make it bigger but not smaller. Does anyone know how to make this smaller? Wait, did that work? Why is there no keybind for it? Okay, there we go. It's all on one screen now. Okay, and so I can take this, and I could just list all those files after cat. So I can cat d license skimp2 scampy udiff, and I can just cat them all together into one big concatenated thing. Why do I want to do that? Well, I have to hash chunks of text, right? So I can cat them together, and I can pipe that into SHA-512-SUM. Okay, and that starts with 1E50. Okay, and that's kind of annoying because I had to list everything. So what do I do instead? Instead of writing out all of the names of files myself, which, to be fair, you could do, right? You're writing Rust, you can do this however you want. We could find star type F, and we'll get the exact same result because we're finding all of the files, and then we're going to concatenate them all together, and then we're going to SHA-512-SUM them. Something I should point out is that this is sensitive to the order of the files, but it is not sensitive to the name of the files. So let's look at this. I'm going to move d.diff to z.diff, and the result's going to change. That's kind of weird. I'm going to move it back, but I'm going to move it to a.diff, and the result's the same again. So this is bad in the following way. It is sensitive to changes in the lexicographical or alphabetical order of the file names, but it is not sensitive to changes in the names of the files. So you can rename a file if its ordering does not change, but you cannot rename a file if it does. That's bad. Somehow you should be preserving this in some other way. So an obvious thing to do is to just add to this thing, right? Let's see, type F. So I got that. And what can I also cat that to? I can just cat it to ls. Let's see. Wait, what? What am I doing? Why am I typing? There we go. You probably also just want to throw in the list of file names as well. There's something, somehow to detect it, right? And it's easy enough to do this. You're just going to want to do it somehow. Okay, so these following slides go through basically the same thing I just showed you. I don't have a great tree. Well, let's see, I do. Course answers. So I have, I think, pretty much the same tree here. Did I gain something? Oh, this has dive on it. This is my JSON implementation of diff. So we have a tree here. If we just naively find, we get a bunch of garbage. If we use find star, we get just the files. Or no, we get the files and folders. If we want just the files, we type F. And then that gives us all of the files, and then we can cat that. Oh, these are backticks. Those aren't quotes. So if I put quotes there, that doesn't work. And backticks mean something in some, I don't know how shell scripting works. It always does what I want it to. Just practice. Okay. That's a lot of text, but here's the cat. Here's the cat, and we can cat into a SHA-512 sum. Okay. If you make any alterations to any of the files, such as adding a new line to the end of them, then you will get a different SHA-512 sum. So how can we demonstrate that? Well, we're going to cat, wait, no, I already did that already. Cat find SHA-512 sum. So that is 397F. And if I change dagger, oh, it's called daggers. That's cute, because it's a DAG implemented in Rust, so it's daggers. It's like, that's metal as heck. Get it? Because Rust is on metal. I'm really on a roll today. I feel like, wait, that's not how you write comments. How do you write comments in Rust? Is this one? I'm a comment. Yay. Okay, and then if we recompute, then we get a different hash, and it is wildly different. And that's from the avalanching and cascading effects that we saw when we implemented SHA-512. Okay, that was fun. I'm having fun. Are you all having fun yet? Okay, cool, that's good. Are you all going to come watch Alien? Think about it. I really don't want to keep mentioning there might be donuts, because it's like very much a maybe, right? Like, I will find out that morning when I wake up if I have time to get donuts. Okay, do you all like, are donuts in? Is there like a more in pastry? I'm really into chocolate croissants, but they're like hard to source. I thought I found a place that I could get them recently, and it turns out it's in Peru, which is like relatively difficult for me to get to. These hashes, the hashes that we just made, this hash right here, I think of that hash as the key, and the commits that I have previously created were the values. So how did this work previously? When I was implementing the no hash version, I just naively appended a commit onto an array, and that's a JSON array, which is the same thing as a Python list, which is the same thing as a Rust vector in JSON world. They're different in any other worlds. So I just appended my commits onto the end, and they weren't in any particular order. Or they were in chronological order, right? But nothing about the hash was in order, right? What you're doing once you hash these is, and you can think about it however you want, but how I think about it is, well, I'm actually going to switch from using an array to I'm going to use a JSON object, which is the same as a Python dictionary, which is the same thing as a Rust hash map, which is the same thing as a Serday map. And so I'm going to have the key is going to be the hash, and the value is going to be the commit that I previously placed directly in the array. So that's what this code looks like. There's one problem with this, which is now you no longer have any idea what order your commits are in. You do get all of the lookup time benefits of using a hash map, right? So it's very fast. But somehow I have to keep this stuff in order somewhere else. So what do? I create one other thing. So previously I just had latest and commit at top level in my SCM. I can sketch this out. So I had SCM, and it had latest, and it had commit. This used to be a list. I had a new list. The list is called hashes. And I changed this to a dictionary. So now we have hashes, commits, latest is whatever you want. I don't know how you store latest. And so this is a design change where I'm now storing the hashes. The benefit of doing this is obviously more work, there's more storage, right? Is that now I can check to see if things are correct, okay? So, why did I draw that on the board? It took me so long to make this graphic, by the way, and I completely forgot I made it. But in fact, I just drew the exact same thing on the board, didn't I? That's like borderline identical, because the ordering doesn't matter. So I think of a commit as a hash table where keys are hashes, it is super confusing to have a hash key to hash table, by the way, because the way you're going to put things in there is you're going to hash the hash and then put it in. And it's going to have inits and diffs, which are the two things I put in there. So these are new files. These are changes to existing files. I intentionally put these out of order. So this is the 1th, and this is the 0th commit. And then I have hashes is an array. Arrays are numerically indexed. And so 0 is the hash of the 0th commit, 1 is the hash of the 1th commit, and so on. So all you have to do when you're trying to change commits is you check the array of ordered hashes to find whichever version you want. So you look it up numerically. That array, given a number, will give you a hash. You'll take that hash, and that hash will be the key to the object storage. Now, something you should think about very carefully really quickly is what data type are those hashes? Because they're hex strings, which means you might end up storing them as hexadecimal strings, and it also might mean you end up storing them as integers. And I would think very carefully about which one of those ones you want to do, because you should do whichever one is easier. It is not dramatically more efficient to store a hexadecimal string as its numerical representation, right? So anyways, think about that if you're doing hashing. This is an implementation decision that is fun to think about. Then you're going to look up the relevant hash in the key value storage of hashes to commits. And surely that's good enough, right? Isn't that good enough? Isn't that definitely good enough? Don't look at the slide here. That's good enough, right? Oh, look, I have ad block. So I had some company over last night. That's not true. My partner had company over, and we casted a fireplace onto our television. And because we did it from YouTube, our fireplace had ads in it. So we got to keep looking at the ads like every 15 minutes while watching the fire. There's no takeaway from that. I just thought it was very Black Mirror. So fun fact, if that's all you did, it's a little bit too easy to still make alterations to this, because all I have to do is recompute a new hash, and then I just have to edit 2 sections of the SCM. But it is quite likely that your friends and family have a Merkle root, because it's really easy to keep Merkle roots around for a lot of repositories. There could be a lot of versions of this out there, and everyone's going to have a Merkle root for it, right? So what we need to do is we need to take all of those hashes and put them in a Merkle tree. And I know what you're thinking right now. You're thinking, wait a minute. How do I gracefully implement a Merkle tree in JSON? That's what you were thinking, right? That's what you were thinking? Okay. Because that's what I was thinking about. Because what you sure don't want to do is you don't want to do you don't want to be implementing this in JSON, right? Oh, I'm going to have something that has hash left, right, and I'm going to do tree traversal through a JSON object. That seems terrible, right? And I know you think this because you are all here for the heap lecture where I showed that you can serialize these data structures, right? So let's go ahead and serialize this. And I'm going to just show you how I serialized it because I thought it worked really nice, and I think it may be non-obvious. And separately, I think it's useful to see instructions on the way some other person would serialize a data structure. So I'm going to serialize this in the manner that I like to call easy style. It optimizes for ease. It does not optimize necessarily for storage space. It is pretty high performance as far as I can tell, but I didn't actually sit down and write a proof about it. Right? It seems fast. So we're going to imagine we have these hashes. We have hash 0, hash 1, hash 2, and hash 3. And they're in order. And we need to throw these things into a Merkle tree. I have the Merkle tree on the whatever side of the screen that is, the side that has the Merkle tree on it. The first thing we note is that we don't need leaves. There's no benefit to leaves at all. I can just directly start embedding portions of the array directly in my Merkle tree. So really all I need is some way that Merkle ancestor can refer to a Merkle successor. Is successor the no, successor is the negation of predecessor. What's the negation of ancestor? Progeny? Scion? Okay, so you got the boomers and you got the youths, right? Okay, so we've got the boomers and the boomers are pointing to the youths, right? Okay. That's not too bad, but this is extremely not JSON right now, because JSON is trees, and this is a DAG. That is 4 arrows pointing into one JSON array. So that is like extremely not a thing. And we really want to keep this thing in order, right? Because somehow we want to just like quickly look up by index the key of a commit. So what can we do? Well, we can recognize the same way that we were storing the last layer of leaves in an array. We can store higher ordered or higher levels, ancestor levels. We can put those in arrays as well, and they're just arrays of sorted length. So what do? I have the array of hashes in order, and then I have the array of hashes of pairs of hashes. So this thing is half as long on average, but it's still an array, and the way you determine what your parent is you divide your index by 2. This is the same serialization technique we used with heap. And we still have a Merkle root. This is just a 2D array. And there are a gazillion ways to store a 2D array. But this is what it was sort of starting to look like in my mind. I have an array, perhaps the outer array, and it is an array of arrays. The first array contains only the root. The second array contains the eldest children. We really got to work on our metaphors in computer science. These are all kind of terrible. And then the last row contains all of the hashes in order. I don't really like that much, so I put all the commits first, and then I put the Merkle tree after them. Why did this make sense to me? Because this is how I wanted to be able to look things up. The latest commit is always the last element of the initial row. By the way, you do not have to go in that direction. You can head append things as well. It's just a little bit harder to deal with the next step. The root is always the only element of the last row. And you can head append, but it's weird. So this is always the latest commit. This is always the root. And what this means is you just always append something to Merkle 0, and then you just probably have some function that you call that is going to update all of the relevant keys. So let's look at an insert example. So I initially had hash 0, 1, 2, and 3, and now we're imagining that I add hash 4 to this. Oh no! Hash 4 is not currently part of the Merkle tree. What are we going to have to do? Well, it has no ancestors, so we're going to give it an ancestor. And how are we going to do that? Well, we're going to hash upward, which now is paradoxically downward because of how this made sense to me. I'm sorry if this doesn't make sense to you. But what I do, I hashed 4, and also its sibling, I don't know, which is currently nothing. So what do? I hash the hash of 4 and null. I did not want to put commas here. I wanted to write this, because by convention, this is how we denote concatenation. But it's easy enough to think of this in one context, which is that I computed a hash here, and I can just compute the hash of that hash and store that higher in the tree. I can also concatenate 2 hashes together. So what are some files I have here? I can cat SHA-512 sum of DAG and SHA-512 sum of dive, and I can SHA-512 sum that thing. So I can concatenate hashes together and then hash the concatenation. So that's what's going on at each of these stages. But realistically, you're probably just writing a function that takes 2 hashes and gives back a new hash. You can do that however you want. So what do? We hash 4 with nothing because there's nothing over here, and we put that in the next row. Oh no, this still isn't a Merkle tree because this middle manager doesn't have a direct supervisor. I don't like that better. Okay, so what do? Okay, I have to add another row to my Merkle tree representing 2D array. What am I going to do here? This old root is going to be unaltered because it correctly captures hashes 0 through 3. But I'm going to have to put something new here. So what do I put there? I hash the hash of 4 and null. We're hashing things up. And actually, probably there should be another null here. I suspect this would be more correct if it looked like, whoa. That's not what I wanted at all. How do I delete everything in a file? Escape, start a file, beginning of line. There we go. Okay. Copy this. I think this isn't how this should look. I think there should be a second null here. And to get Python syntax highlighted on this, you'd have to do none. Okay, it's still not highlighting. So you should always be tossing nulls at the end. So I think properly there should be a null here. Maybe it doesn't matter. You can think about it. You just have to do things consistently. You also definitely don't have to put a null here. Or maybe you just treat null as literally being the same thing as nothing. I don't know. Okay. And then the last step we have to do is we just add the new root. And the new root is just, you concatenate this thing to that thing, and then you hash it. And then you keep doing this. Now, if you added 5, it would be pretty easy. What would happen? 5 goes here. I add something here, and I add something here. You add 6. Now there's something here, but we don't add a new thing in the row. So you don't add new rows very fast. So you'll have, in the number of commits, you'll have the log number of rows. This is how I conceptualized it if you put this in separate arrays. My first array is the hashes in order. My second array is a bunch of intermediate hashes. My third array is a bunch of intermediate hashes. And then the last thing is a hash that is dependent on every single value in the entire hash table. Keeping these intermediate values makes it easier when there's different versions on different systems to compare against them and make sure there's everything is coordinated up to some perhaps most recent commit, and you just like look at whatever the relevant portions of the tree would be at that time. This means that every time you add a new commit, you have to compute a number of hashes. So you have the cost of hashing the entire size of the commit, which could be quite large, right? If you're maintaining a gigabyte of source code, that will take some amount of time. I wonder how long that'll take. I don't think I have anything that's that big. I don't know, do I want to do this? I can just hash every binary on my system. That'll take a while. Oh, no, it didn't. Okay, so apparently it's fast. Okay, you will compute a hash for log of the number of commits. This cost seemed fairly reasonable to me. I don't think that's too high, and I'm guessing that's what Git does internally. Also, if you have ever done a Git push, let's see. I don't have any repositories on here I want to push. It does all this delta compression stuff, and then it's moving things like Git push is slow by the standards of modern computers. So it's doing tons of hashes in the background, and so I didn't feel too bad about paying some performance costs. It is not unreasonable to do this heap-wise. You can put this all in an array. The way I was thinking about doing that is I was going to head append. I was going to head append new commits, so the commits go at the beginning. And then the tail was going to build out and have the new Merkle root at the end of the tail. That's how I was thinking of it. So you just kind of serialize it in that direction. It just seemed way nicer to have a separate list of commits, and once you have a separate list of commits, it makes sense you just implement the Merkle tree directly on top of it. So that's what I did. And I also thought it was really convenient to just always update the last element of each array. That was really nice. Last application. Oh, we're going to end again early today. Oh, no, I'm supposed to give you time for course evals. Okay. Signing is easy. Once you've done ED 25519, the math is hard. The actual work is easy. I just added something new to each commit. Anyone that's committing, you look up what their private key is. Mine always lives in... Should I show you my private key live on stream? That seems crazy, right? Okay, well, so here's my private key. It's ID underscore ED 25519. I'm sort of unwilling to just cat that while I'm on YouTube. And here's something that I love about this implementation. So if I sh, if you autocomplete this and press enter, it will show the private key first. Why is the private key the one that is easier to accidentally see, right? I have to proactively type pub. You're allowed to see this one. This is my public key. So anyway, there's my public key. What does this mean? This means that you can pretty easily have your Rust thing go out, look up the key, and presumably you have a key that you're like at least using for GitHub or something, right? Like, and if not, if you need to learn how to generate keys, I will send you the link to my thing about generating keys. So you can just go out, you can look at the key, you can sign something, and I think you can sign something without ever looking at the key, right? And this is an extension assignment, so you are on your own for this. And then what do? You write the public key. What's the public key? Right there. No problem. Very easy to write. That's not that much information, right? And then what do? You use this public key to encrypt what hash? This hash. So you encrypt that using the private key. Someone with the public key can see that. They can decrypt it and see it's the same as the hash of the commit they're looking up. And then you can be confident in what? There are no tampers to the commit, and also the person who owns that public key is the person that made the commit. And that seems super easy to me. Once you implement all of these hashings, they are completely useless, and you in fact will not really probably be able to convince yourself that they work until you do a revert. And when you do the revert, make sure you recompute the hash once things are written to the file system. Make sure you decrypt the signature and guarantee that the public signature or the digital signature is completed correctly. And you check both of those things against the hash of the commit. And if there is a miss, somehow you have to reject the commit. And what I would do is I would rewrite latest back if that happens. How do you test this? Were I you, I would just come in here and edit one of these commits, and it would be pretty easy to do that. This thing isn't particularly pretty printed, but it could. So maybe I want to change diff helper to my diff helper. I'm currently allowed to do that because I'm not hashing anything. If you do this, it should explode and never work again, because no one should be able to tamper with the plain text. What is? Oh, I have the complete text of the license in here. See? Isn't that fun? Okay, so wait. Oh no, where am I typing? Okay. Sometimes my brain hits escape and my hands don't hit escape, and it takes a while for my brain and my hands to figure out what each other's doing, right? That's how I check this. You will know hashing works if you can edit either your file system or your JSON that represents all of the commits, patch something, and then it explodes. That's the end. I am seeking exactly 4 researchers next term and next summer. Next term, there will be a 2-credit-hour remote synchronous research training course administered by CRAN, which is the computing research. I don't remember what it is. They're awesome. That's not it. See here? No, maybe it's something else. It's these people. CRA. It's just CRA. It's not CRAN. The way this works, as far as we can tell, we did this successfully last year, is you complete the research training course with them, which I will help supervise. I will give you a paper from my research group to read, and then we will meet once and complete a contract on how you would plan to conduct research with me over the summer. The semester ends, they will give you basically a grade based on whether you attended the courses or not. Then going into the summer, if you passed the course and I'm impressed with you, which I will be, we can apply for REU funding to this organization. Why are we doing that? Okay, this is extremely secret. It's paid for by Google and not the NSF. Which means that if the NSF shuts down this summer, your REU is still funded. Very few REUs are like this. But this means we have to go through a different process. The way this works for faculty is we have a team of between 2 and 4 researchers that go through this undergraduate research course together, and then they apply. To our knowledge, everyone that has applied for funding has gotten it. So it does not seem that selective, which is good. If more than 4 of you are interested in doing research, I will talk to my colleagues in the department and try and pair you with them. And also, if you don't want to do my research, which is like vaguely related to this class, but not exactly, we can talk about it. I will try and find someone else for you to work with as well. I think it would be nice to have between 10 and 20 researchers on this summer. That is a lot of you. So think about it. If you are graduating, don't do this. You can read more about your 2 PhD. The decision point on this is, I think, early February, when you have to have signed up for the research class. And I will have to put a team of you together because you have to do it as a team for it to work. So I'm interested in doing this with you if you're in this class, and I will start recruiting some of you aggressively if I don't hear from you soon. So look forward to that. Thank you. Have a great semester, or you already had a great semester. Enjoy the final. You're supposed to fill out the course evals, so you can put whatever in there you want.
Should we send you an email?
Yes. Express interest early and often.